Okay, we're doing the honors physics CAPM practice number 4, problem about a motorcycle chase, and we're going to use algebraic methods, which means that we're going to use diagrams to set up our relationships. So it kind of takes forever to draw motorcycles, so I'm just gonna have letters here. So Clay has his velocity of 30 meters per second, which is a little over 60 miles an hour, so he's moving. I'm going to call positive to the right. And then Clay gets, down the road, still going that VC. And Clay is going to move some distance that we don't know. You could call that a delta x if you like. I'll stay with distances here. It doesn't really matter at this point. Jax's initial velocity is 0. We're looking for, or modeling the first interval first, where we talk about how he gets up to Clay's speed, and when he does that, we have pretty equal v vectors here, but he's going to be, v final is vc, he's going to be behind him at this point, so Jax will not be caught up just because they're going the same speed, because Clay was going that speed the whole time, and Jax just now got to it, so he's definitely behind. These do have the same delta t, however, and Jax has an acceleration going that way. Clay's acceleration is 0. So I have all 5 things labeled here and all 3 things labeled here, actually plus 1. This is a CVPM motion, this is a CAPM motion. So I have 5 things to label here and 3 to label here. So the delta t's are the same here, and the VFs are the same, so I'm going to use that to my advantage. Well, really all I'm going to do is get an expression for Jax's acceleration. So I'll use VF is VI plus A delta t. Jax's VI is 0, so that can go away. That's a good exception to no numbers till the end. You can put in zeros. That's fine. And VF is really VC. You could also get this by just using the definition of acceleration. That would have been fine. Alright, so we want this expression. We're not going to plug in the number because we're going to go no numbers till the end. Now I'm going to diagram this thing looking at the whole race. Okay, so Clay's starting deal is the same. He's going to get further down the road here. Still the same VC, still no acceleration. Okay, so I'm going to call this total distance d, which is unknown, and this delta t is unknown. I'm going to call this a different delta t. I'll call it delta t total. Jax starts still at 0. I'm still having that be the same starting point. But he ends, and he'll be going faster than Clay at the end because he had to catch up. Okay, and he has a VF there. This time, though, they have gone the same distance because he's caught him. And they, of course, have been moving for the same amount of time. So I'm going to apply this acceleration to this interval because it's the constant acceleration. And now I'm just going to use some algebraic models here. So CVPM, there's not a lot of choice here. The distance that Clay goes is his velocity. So if you see there, his velocity times the delta t total. And the distance that Jax goes, which is actually the same d, so that's going to help us out. I'm going to use this model. And Jax's VI is 0, so that term will go away. Now these are equal, so I'm going to use this for d and solve. So VC delta t total equals 1/2 A delta t total squared. And I'm going to sub in for A. So VC delta t total is 1/2 VC over delta t, the original delta t, times delta t total squared. And now we can do some simplification. I can cancel the VC's because there's one in every term. I can cancel one of the delta t totals. That leaves this side as 1. Okay, this whole thing goes to 1 when all that's canceled. So I get 1 is 1 over 2 delta t total. Solve delta t total is 2 delta t, which is 30 seconds.